Hello everyone, and welcome to OneClass. My name is Jeff Krause. I have a PhD in chemistry, and today I'm going to run through a few undergraduate, high school level chemistry questions. So here's our first one. Draw Lewis electron dot diagrams for the following species. So here's our first. First on the list here is arsenic trihydride. So if we check in the periodic table, arsenic is underneath nitrogen. So this guy has 5 valence. And this guy always has 1 valence. So times 3 is equal to 3 total. So then the total valence electrons are 8. So the way I always draw these is just to hope at first that it follows a simple pattern. And then to correct afterward if not. And so this looks good. So it'd be a trigonal pyramidal structure where the wedges are out of the board and the dashes are into the page. So that'd be a trigonal pyramidal. Okay, and then I guess it's just electron dot diagrams, but oh well. Okay, so then HOCl, we've got 1, 6, 7 for each of the valencies, so then 14 total. Okay, and then again I'm just going to assume simple and then correct afterward if it doesn't work. So that looks good. And we've got our 2, 4, 6, 8, 10, 12, 14, so that looks good. And so that's our molecule. It's linear. Okay, and then Kr F plus, Krypton has 8, fluorine has 7, and then the plus charge is -1. So -1 of our total electrons, so 8 plus 7 is 15, -1 is 14 total. And then in this case, I would say it's fairly obvious that for Krypton to bond, we have to take an electron away from it. So I'm going to give it 7 instead of 8. And then for fluorine, I'm going to give it its full 7 because it's bond. And then if we check the charge here, we count the number of electrons around Krypton. Well, it's 7, which means it has a plus charge. So that would be Krypton fluoride, with a positive charge on the Krypton here. Okay. PO2, Cl2 minus. Okay, so then we've got 5 electrons here. 6 times 2 equals 12 there. 7 times 2 equals 14 there. And then the minus charge is going to be another +1, so an extra electron. So then we've got 5 plus 1 is 6, plus 12 is 18, plus 14 is 42. Wait, what did I just say? 5 plus 1 is 6, sorry, plus 12 is 18, plus 14 is 32. There we go. I don't know what kind of weird math I was just doing. So we should have 32 total. And it gives us that the phosphorus is the central atom. So again, I'm just going to kind of assume that things are going to be simple and then correct afterward. Except we need 4 bonding partners. So I'm going to go ahead and give our phosphorus its 4 bonding partners. And then put our oxygens in around it the way they normally would be. And see what needs extra electrons. Okay, so at this point now, we've got our single bond here, our single bond here. If we count our electrons up, we've got 2, 4, 6, 8, 2, 4, 6, 8, so that's 16 over here. And then we've got 2, 4, 6, 7 here, and 2, 4, 6, 7 here. So there's 14 over here, so that's 30, so we're missing 2 electrons. So we could go ahead and just plunk them here and here, which would give us our bonds here and here. Okay, and then now we've got a negative charge here, a negative charge here, because if we count the number of electrons around oxygen in both cases, it's 7, but oxygen normally wants 6, so that's a minus charge. And then if we count the electrons around phosphorus, then it's 4, and phosphorus normally wants 5, so that's a positive charge. But we've got full octet everywhere, so that looks pretty good. The only thing that I will point out is that phosphorus can become hypervalent because it's lower in the periodic table, meaning octet doesn't matter that much. And so this structure might actually be more plausible, even though the octet rule is not satisfied. But because in this structure we now have the negative charge, we now only have a single negative charge on the phosphorus in the center, and therefore the charge isn't distributed or split across the molecule in such a great amount. But in any case, both of these structures are viable, I would say. Okay, let's check through the solution here. So there's arsenic trihydride, which basically is what we had. It's a little drawn funny, but it's okay. HOCl, just backwards from how I drew it, but that's the way we did it. KrF plus, that's just kind of wonky. There's 2, 4, 6, 8, 10, 12, 14, 15 electrons here. But KrF plus should only have 14, so that's just incorrect, I would say. As there's not the right number of electrons. We've got 2, 4, 6, 8, 10, 12, 14, 15, but as we already counted, we need to reduce the electrons from 15, which is the normal amount, to 14. So that structure is just not correct. And then, well, the fluorine, it's got fluorines instead of chlorines, but that's okay because they basically have the same valence. I think that is a viable structure. Yeah, I could have drawn that as well by looking at it, because we could have. This is basically popping this up, which actually should be another viable structure in retrospect, because we've still got the charge. We've still got the charge localized on only one atom. It being oxygen. Yeah, so that would be fine as well, actually. Phosphorus is still hypervalent because it has 10 bonds, but that's fine. And the charge is only on one atom, so I would think would be happier than in this fully charge separated case. So it's just the fluorine should be carbons. I'm going to have to say it's incorrect though, just because the KrF plus solution. So has too many electrons. Also PO2Cl2 structure uses fluorines. So I'm just going to say it's incorrect because the FKR, or the KrF solution there, but for the most part it was correct. Okay. Draw the Lewis structure for Tellurium chloride, and so forth. So I'll go through each one, and then we'll go through the questions that it's asking afterward as well. So first, just the structures. So for Tellurium chloride, so this guy has 6 electrons. Each of these contributes 7. So that's 28. So then we've got a total of 34 electrons. So I'm just going to draw the same way I kind of normally would. The only thing is, we need 4 bonding partners, so we might as well make sure that's there. And then a lone pair. And so tellurium is far enough down on the table that it can become hypervalent, so there's not really a concern about having the lone pairs be in any particular orientation. We already know that it can do it, so might as well just set it up to bond how the molecule shows it's bonding. Alright, so there's our bonds to chlorine, and so we've got a single lone pair and four bound species. So that's for 5 connected species, it always has this kind of structure, where this is coming out of the page, and that's the lone pair. And then we got chlorine, 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 chlorine. All right, so there's our structure, and so this is a seesaw. It also wants the hybridization, so we're going to go through that. So for hybridization, we would always use an SP D notation, where we drop the D if we don't need it, but basically the numbers, where if there is no number, it's a 1, adds up to the number of species bound, and we could only have 3 p orbitals. So in this case, we need 5 species, including the lone pair. So 1 plus 3 is 4, so we need at least a single d orbital to give 5. So the hybridization is sp3d. And then the angles in here are going to be, because of the lone pair, we're going to get repulsion. So this is going to be less than 90. And the angle, how do you indicate this? So this angle in here, it normally would be 120, but it's going to be less than 120. Again, because of the lone pair, which is going to be repelling. Okay, so ICl5. So this guy has 7, and then these contribute 7 times 5 is 35, so total is 42. Again, ID normally would have 7, but obviously it has 5 bonding partners, so we're going to need to put those in. And then it'll have a lone pair left over. Alright, I'm making these bonds progressively different sizes, but it's okay. If we count everything up here, right, so there should be 2, 4, 6, 8, so 8, 16, 24, 32, 40, and then 2, so that's our full electron count. This kind of looks like garbage the way I've drawn it, but I'm going to draw the full structure, so I need 6 bound species, so that's going to be our general octahedral shape. And so I'll have the lone pair going up, a chlorine going down, and then the other ones will all be out of the page and into the page. And because of the electron repulsion, everything's going to be pushed down, so this is actually going to be less than 90 and less than 90 here, or actually greater than 90 here. Yeah, because these will be pushed apart as it goes down. So these guys will kind of umbrella down. And so an iodine in this case has 6 bonding partners. So following the same rules, we need 1 plus 3 plus 2 equals 6. So sp3d2. Okay. PCl5. Phosphorus has 5. Each of these contributes 7 times 5, which is 35, so 40 total. Our phosphorus has 5 bonding partners, so we might as well split all 5 of the electrons. Okay, I'm just going to fix this chlorine. There. Okay, and so we have our 40, 8, 16, 24, 32, 40. It's bound to 5 partners, so we're going to use our generic 5-member structure here, where these are coming out of the page, into the page, straight up. Okay. Then we can put our electrons, our lone pairs on here. All right. Sec. Okay. So this guy's perfectly symmetric now. It's I suppose I should have been putting the names on there too, but maybe we'll go back through and do the names. But I'll continue with the angles and everything. So these angles are going to be 120, and these angles are going to be 90, because it's perfectly symmetric. And then for our hybridization, we need 1 plus 3, as that only goes up to 3, so we need 5 total. So 3 plus 1 is 4, plus 1 is 5, so sp3d. Okay, and now I'll do the next one. So Krypton Chloride. Okay, so Krypton has 8. Each of these contributes 7, which is 28 total. So then the total is 36. We already know that the Krypton needs 4 bonding partners. And then might as well plunk in the lone pairs, just like that. Okay, and then bond them. Okay, that looks good. So we've got 8, 16, 24, 32, and 4 is 36, so that looks good. It's got 8 bond. The Krypton has 6 species around it, making it our general octahedral structure. So I'm going to go ahead and put the lone pairs above and below. And then I'm going to put the chlorines in the plane. Like that. And they're lone pairs. And again, the wedges are coming out of the page and the dashes are going into the page. Okay. So these angles in here are going to be 90 degrees. And since we have 6 bonding partners, we will need 1 plus 3 plus 2 to equal 6, so sp3d2. And then for the last one, Xenon Chloride. So we've got 8, and 2 times 7 is 14. So then in total we have 22 electrons. So our xenon has 8, but obviously needs 2 bonding partners. So then there's our 8 electrons. And there's each of the 7. So we've got 8, 16, and 6 is 22. So we've got 5 partners around xenon. So I'm going to go ahead and plunk these on the equator. Okay, and so our molecular structure is linear, but Xenon is bound to 5 partners, so sp3d. So 1 plus 3 plus, so that's 4 plus 1 is 5. So it's just sp3d hybridized. Right, and the bond angle here is 180. Okay, so now going through these questions now. Which of the compounds exhibits at least one bond angle that is approximately 120 degrees? So I'd say there's the PCl5, definitely. So here we have a bond angle that's 120 degrees. So I'm going to summarize this at the end here. Oops. 120 degrees. So PCl5 was 1. And so these are all about 90. Tellurium chloride would be roughly 120, but a little less because of the lone pair. But I'm going to throw that in the list as well, just because I'd say tellurium chloride are less than 120 degrees, but it's closer than the others. Not that it necessarily needs to have more than one. So which hybridization? sp3d2. So we went through and did that. So so the Krypton, the KrCl4 species had that hybridization, and I believe there was another one. The ICl5. And I don't think there was another sp3d, sp3d, and sp3d. Okay. And then which of the compounds have a square planar structure, and which of the compounds are polar? So let's take care of that while we go through. So this one's seesaw, and because of the lone pair, it is asymmetric, so it will be polar. Right, so there will be dipoles here, which won't exactly cancel because the structure would be pushed out of, well, not just because of that. If you add up the dipoles, they won't cancel, so it's polar. Here we've got minor dipoles between iodine and chlorine, and it will point towards the iodine. And again, it's asymmetric, so it will be polar. And the structure here is square pyramidal. Okay. Now this guy is trigonal, bipyramidal. Okay, and because of the perfect symmetry, this will be non-polar. Right, so far the first two have been polar, so this is the only one that's non-polar. So this structure is square planar, and because of the symmetry, will be non-polar. And this one here is linear, and because of the symmetry, is non-polar. Okay, so which of the compounds are square planar? So for square planar, that was only KrCl4, and polar, that was the first two, and then the latter three were nonpolar. Okay, so going through the solution given, this looks roughly like our structures. So TeCl4 and PCl5 should be roughly 120. KrCl4 and ICl5 should be sp3d2 hybridized. KrCl4 has a square planar structure. TeCl4 is polar, ICl5 is polar, while PCl5 is non. KrCl4 is nonpolar, and XeCl2. So the only polars are these two, so that looks good. Let's say this is correct. Okay. Alright, how do you find density in the ideal gas law? So starting off with the ideal gas law, PV equals nRT. And now density is mass over volume. So we need to get mass in our in our ideal gas law. So our number of moles is mass over molar mass. So we can put that in. So inserting this into here, we have PV equals M RT over M. And now we can rearrange to get mass over volume. So pressure times molar mass over RT is equal to M over V, which is equal to our density. So from the ideal gas law, density is pressure times molar mass over the ideal gas constant times temperature. Checking through the solution here. Pressure times molar mass over RT. So that looks good. Good. The following reaction has an activation energy of 262 kilojoules per mole. At 600 Kelvin, the rate constant is 6.1 times 10 to the minus 8 per seconds. What is the value of the rate constant at 730 Kelvin? So this is an application of Arrhenius' equation, which states that our rate is some factor times e to the minus activation energy over RT. And just for completeness, although R is fine to use here, this sometimes is written as KT. But K and R, K being Boltzmann's constant, they're the same constant, just different units. Okay, so we're going to write out some of the values here. So we have K1 is equal to 6.1 times 10 to the minus 8 per seconds. T1 is 600 Kelvin. K2 is our unknown, and T2 is 730 Kelvin. So if we write this out, we have K1 is equal to A e to the minus EA over T1, and K2 is equal to A e to the minus EA over RT2. Now if we divide these two, K1 over, I better make sure I follow my solution a little bit, K1 over K2, okay, so then these A's will cancel. And dividing exponentials means you can subtract their factors. So you end up with an exponential minus EA over R, 1 over T1 minus 1 over T2. So we subtract them, which would turn this positive, but if I'm taking a negative EA over R out, that will turn it back to negative. So there's our expression there for dividing the rates. And then now we want to solve for our K2. Or I guess what I did was just solve for this. So K1 over K2, so inserting our values. I'm going to use, so the EA given is this 262 kilojoules per mole. R is 8.314 joules per mole Kelvin. So we're going to need to multiply by 1,000 joules per kilojoule here, just to get rid of the kilojoules, and the joule will cancel there, the per mole will cancel. Giving a Kelvin up top, and then this is 1 over 600 Kelvin minus 1 over 730 Kelvin, meaning everything's just going to, all the units are going to cancel, which is good. When we take an exponential, we want it to be unitless. Running this all through our calculator, we get e to the minus 9.3532, which is 8.6687 times 10 to the minus, no, times 10 to the minus 5. Okay, so then rearranging for K2, K2 is K1 over 8.6687 times 10 to the minus 5, which equals this 6.1 times 10 to the minus 8 per seconds over this factor, which comes out to be, and rounding to two significant figures, because that's all we were given in the K1, 7.0 times 10 to the minus 4 per seconds. Okay, so there's our K2 through from the Arrhenius equation. So that's our rate constant at 730 Kelvin. So going to the solution here, so you could solve for the prefactor, but you don't need to. And then you can, so that's what they did here, was solve for the prefactor and then use that in Arrhenius' equation to solve for the K. But it comes out to be 7.0 times 10 to the minus 4, so that looks good. All right. So it wants us to calculate delta S for this reaction, and it gives a table of values, but I'll copy them out. So we've got 2NO gas plus O2 gas goes to 2 NO2 gas. And it gives a table of S naughts. So for NO2, our S naught in joule per mole Kelvin is 240. For O2 is 205.2. And for NO is 210.8. So given a table of standard entropies, we can calculate delta S as the sum of our standard entropies for products minus our sum of standard entropies for reactants. And we include our stoichiometric coefficients. So in this case, we have 2 NO2 molecules. So we would use the 240 for the NO2 standard entropy. And now we would subtract the sum of the reactants. So it would be 2 times 210.8 for NO, and then plus the oxygen 205.2. So then running this all through on our calculator, negative 146.8. Okay, so that looks pretty good. Going through this, so we just run through this equation and we get negative 146.8 using the given values. So that looks good. What is the Lewis structure of NBr3? All right, so NBr3, nitrogen has 5 valence. Each of the bromines contributes 7, so that's 21. So in total, we have 26 valence. I'm just going to try it the simple way and then correct after. And so this looks good. We have all of our electrons represented, and we can get our bonds. And so then this has 4 bonding partners, so it's going to be drawn in the regular tetrahedral structure with the lone pair going up. And so this is a trigonal pyramidal structure. And all of our electrons are there, so that's good. And so there's our structure, so that looks good. Solution's correct. Okay. Douglasite is a mineral with the formula 2KCl, FeCl2, 2H2O. Calculate the mass percent of Douglasite in a 455 milligram sample if it took 37.2 mils of a 0.1 molar silver nitrate solution to precipitate all the chlorine as AgCl. Assume the Douglasite is the only source of chloride. So to start off, we're just going to say that this mineral is going to completely dissociate in liquid, or in water, I should say, to give us each of the aqueous ions, so 2K plus, so if we count the chlorines, so we've got 2 chlorines here plus 2, so 4, plus Fe2 plus, and actually that's all the ions. Okay, so that's our source of chlorine. And then the silver nitrate solution, or the silver nitrate reaction, is going to be this to give us silver chloride plus nitrate. Okay, so then we had 37.20 mils of a 0.1000 molar solution, and it said that this reacted completely with all the chlorine. So that means since we have a 1-to-1 ratio here, right, so that the coefficients here are 1s, that means that we have exactly the same amount of moles. And so once we find the moles for silver nitrate, we have the moles for chlorine. So so our moles are our concentration. And I should put that actually, instead of in molar, in moles per liter, times 37.20 mils, so our volume. To get the liters to cancel, we're going to multiply by 1 liter over 1,000 mils. So that'll cancel that, and I'll cancel that and leave us with moles. And then running this through on our calculator. So 3.72 times 10 to the minus 3 moles. And so as we said, that has to be equal to our chlorine number of moles. And then from this equation, we can see that for every 1 mole of our Douglasite, we get 4 moles of our chlorine. So that means that our number of moles for this structure is our number of moles for chlorine over 4. Right, so 1 mole gives us 4. 1 mole of Douglasite gives us 4 of chlorine, so that means for each mole of chlorine we have a quarter for the Douglasite. So that's 3.72 over 4, which comes out to be 9.3 times 10 to the minus 4 moles. Okay, so now we have our moles, and it wants us to know mass, or it wants us to give a mass percentage of 455 milligrams. So to get a mass, we need our molar mass. And so for this, I'm going to use the molar mass for potassium as 39.0983, molar mass for chlorine 35.453. I'll put in units here. Molar mass for iron of 55.845. Molar mass for oxygen 15.9994. And molar mass for hydrogen of 1.00784. Okay, so then molar mass for 2KCl, FeCl2, 2H2O is 2 times our molar mass for potassium plus 4 times our molar mass for chlorine plus our molar mass for iron plus 4 times the molar mass for hydrogen, and plus 2 times the molar mass for oxygen. And if we put in the relevant values and run this through, we'll get 311.88376 grams per mole. Okay. So then now using our molar amount and our molar mass, we can solve for our mass of 2KCl, FeCl2, 2H2O. And so that's going to be our molar mass, 311.88376, times our number of moles we found, which was 9.3, times 10 to the minus 4 moles, which comes out to be 0.2901 grams, or 290.1 milligrams. So it wants a mass percentage of a 455 milligram sample. So that would just be the mass over the mass total times 100%, which is 290.1 milligrams over 455.0 milligrams times 100%, or 63.75%. So there's our mass percentage of Douglasite in our 455 milligram sample. Okay, so we need our molar mass, which they solve for similarly. Comes out a little different because we use a little different molar masses, but that's okay. So it comes out to 0.29 grams. I don't see where they solved for the moles, but I guess that's okay. Oh, okay. Yeah, they just put it all together. So, yeah, so there's the 1/4, and there's all the stuff. So they just put it all in one line, and it comes up to 63.75. So that looks good. We're a 0.01% different, but I assume that's just from different molar masses. Okay. How do you calculate the ionization energy in kilojoules per mole of the helium plus ion? And it gives us that an H-like ion follows an hydrogen-like energy level structure. Where this here is our atomic number. So for helium, this would just be 2. So for helium plus, our energy levels are given by this equation. Okay, so ionization in a simplistic picture, if this is the nucleus and this is our electron orbiting, ionization is just the energy difference in taking the electron to infinity. So removing the electron from the atom, or put another way, or in an equation form, ionization energy is just the energy at infinity minus our end state energy. We set this energy to 0, which makes sense because if you look, these energies are all negative. And so then it's just minus the energy of the state. So quite simple, the ionization energy is just the negative energy of the state. And so for putting in the hydrogen equation, it just comes out to be positive, these values. Now, applying it, right, so helium plus is a one, just has a single 1s electron, so N would be 1. So the ionization energy for our 1s state would just be 2.18 times 10 to the minus 18 joules times 4 all over 1 squared, which comes out to be 8.72 times 10 to the minus 18 joules. And that's it. So looking through the solution here, it reaches it, it becomes ionized. No, so this actually isn't right. So we can calculate the ionization energy as, oh, okay, no, okay, it's fine. So it's not just, it's not when it reaches a higher state, it has to be actually taken to infinity. So as n goes to infinity, basically this goes to 0. And so the first term goes to 0, and so we just get this. Okay, that's good. And okay, they add some stuff. So just the first bit is not quite correct, but they did it properly. But I'm just going to say it's complete removal of electron, not just excitation, but largely it's correct. Okay. This is kind of a unit analysis question. And so it asks, or it states, to take this definition of the coefficient of volume expansion to be 1 over V dV by dt. Nope. dV by dt. Temperature, so derivative of volume with by temperature. And it says to show, show that beta is 1 over T with the ideal gas law. So the ideal gas law is PV equals nRT. Solving for volume, volume is nRT over P. So then dV by dt is nR over P. And now plugging these into here, we've got beta is, so 1 over V is just going to be P over nRT. And then dV by dt is our nR over P. So then these guys cancel. And this is just 1 over T. So that's what it asked us to show. And then it asked us to compare to measured values for beta in air of 3.67 times 10 to the minus 3 and beta for helium of 3.665 times 10 to the minus 3. And these are at 0 degrees Celsius. So for 0 degrees Celsius, T is 273.15 Kelvin. So beta, regardless of the material or what it's composed of, beta is just this 1 over T. And that comes out to be 3.661 times 10 to the minus 3. And looking at these values for air and helium, I'd say it looks pretty good. So this simplistic derivation for our volume expansion coefficient works pretty well. Okay. So looking to the solution, yeah, so that looks pretty good. So I'd say that's correct. Oh, I'm having a time here. Uh-oh. Come on, I believe in you. Oh, I broke it. All right. Did not like this? No, liked it. Let's see if I can trick it a little bit. Okay. No. Okay. So that's unfortunate. Okay. I guess I'll just call it here then. All right. I guess I'll just say that's enough for today anyway. Thank you for watching. If you enjoyed this, please subscribe to OneClass. If you want to leave questions, you can follow the links in the comments. This has been Jeff Krause.